first talk will be given by Professor Emanuel Peled from the School of Chemistry at Tel Aviv University. And the title is Sub-Monolayer, Platinum Shell on Ruthenium-Core Nanoparticle. Well, you can read the end of it by yourself. The reason why I said the first part is because I'm very proud that now I know what MeOH stands for. So that's the only thing I asked before. Please, Emanuel.
Okay. Good morning. You saw the title. First, I'd like to acknowledge my student, Dima Kaplan, who did most of the work, and another student, Mital Alon, and two experts from the Center of Materials, Burstein and Rosenberg, that carry out the XPS and the XRD characterization. I will start with some introduction on fuel cells and direct methanol fuel cells, DMFC, and direct ethylene glycol fuel cell. I will talk a little bit on the electrochemical oxidation of methanol and ethylene glycol. And what was found in the literature is that platinum is not a good catalyst for alkyl electro-oxidation. And today they are using platinum ruthenium as the best one for methanol. For ethylene glycol, it is not known yet. I'll present the potential advantages of a ruthenium-core, platinum-ruthenium shell, nanoparticles, catalyst, and discuss how to determine the shell structure and composition. We have two goals in this research. One is purely scientific, and that's to study the correlation between shell composition and structure and catalytic activity and durability. And the other one is economic or practical or technological, reducing the catalyst loading by developing more active catalyst per gram of platinum or per dollar. So first, what is a fuel cell? A fuel cell is a unit or device that converts the chemical energy that gives free energy of the reaction between fuel and oxidant directly into electrical energy, like delta G equals minus NFE. And the difference between a fuel cell and a battery is the battery box contains all the chemicals, and when they are gone or discharged, you have to buy another one or charge it. In a fuel cell, you have only the electrodes in the cell, and as long as you flow or feed the fuel cell with fuels and oxidant like air or oxygen, then you keep getting power. There is a very interesting issue that, in difference from Carnot cycle, the energy conversion efficiency of a fuel cell or any electrochemical device can be 100% in terms of delta G, as you see on this equation, but technologically we are paying for delta H of a fuel, and then for the efficiency of a fuel cell or a battery is delta G over delta H. Now it's interesting that delta G can be higher in absolute value from delta H and can turn the entropy of the surrounding into an electrical energy direction in 100% yield. So we can get thermodynamic yield of a battery or fuel cell that larger than 100%, can be 110, if delta S is positive. More than that, if delta H is 0, that means the chemical reaction produces no heat, but the entropy increases during the discharge, you can turn this entropy into directly electrical energy with 0 delta H, which is interesting. It's not practical, but interesting. Okay, this is the way direct methanol fuel cell works. The heart of the fuel cell is the membrane, which is proton-conducting membrane. On both sides, on right and left, you have nanoparticles of platinum or platinum alloy. On the left side, we feed methanol solution or ethylene glycol solution. and it's oxidized to form CO2 and 6 protons, 6 electrons. On the right side, we feed oxygen or air, and we got on the right side water vapor that's coming out. The cell voltage thermodynamic is about 1 volt. Practically, it's much lower. Why methanol is not hydrogen? Usually.
How do you make a choice?
Okay, so most of the fuses today, or historically, were using hydrogen versus oxygen or versus air. And today there are a couple of hundreds of electric vehicles running on hydrogen with a fuel cell in the size of 100 kilowatt. The issue that hydrogen is a gas, and it's different to use it. And either you cool it, liquefy it, or you compress it. But methanol and ethylene glycol are fuels that you can directly convert in electrochemical cell. Other fuels not. And actually, until about 5-6 years ago, only methanol was known. We were the first to prove that ethylene glycol and some of its compounds can be converted 100% into CO2. A fuel as organic molecule that you can convert into CO2 by 100%. If it's not 100% and you have residue, then it's not a fuel because you have to change the solution each time. So therefore, methanol, ethylene glycol are fuels. They are liquid, easy to carry them, and so on and so forth. Now, about 5 years ago, we developed, with a budget of $1 million, a unit that powers a laptop. And what you see here, it's a direct methanol fuel cell. And it's called direct because you feed directly methanol. There are other fuel cells that you convert methanol and water into hydrogen. This is indirect methanol fuel cell. So therefore, it's called direct. So what you see here, this is the stack of about 20 cells in series combination. This is the methanol tank. So you see the methanol tank is quite small relative to the unit. Here it's a mixture chamber and phase separation chamber, air compressor, and 2 pumps. Now, why do we like to use or to replace lithium-ion batteries with direct methanol fuel cell or direct ethylene glycol fuel cell? There are 2 major reasons. One, they have higher energy density for long missions or long use, and there is fast refilling. In order to charge a battery of your computer, you need at least 2 hours or 10 hours, but to refill water, it's a few seconds. Now, this is an important slide, show you where and under what condition direct methanol fuel cell is better than a lithium-ion battery. On the lower end, you see here, this is the unit we actually developed, and it can produce 12-watt net, so it can run a small computer. And what you see here is a plot of the energy density in terms of watt-hour per kilogram versus the operation life. Now, if you have a lithium battery for your computer and it works for 5 hours, you want 10 hours, you need 2 batteries. That means you double the weight. So you keep the energy density constant even if you want to work more times. Now, with a fuel cell, there is a separation between the power unit and the tank of the energy storage unit. So this is, let's say, this is the power unit, and here it is the tank. So if I want to work two times longer time, I need to increase the size only of the methanol tank. Therefore, as I'm using it for longer and longer duration, the energy density becomes better, and I can get, let's say, about 500 watt-hour per kilogram after 30 hours of operation. That means for the same, if you're using a smaller one, it will be easier and lighter than lithium-ion battery. So this is the general, it was analyzed for our unit, but in general, if you have a fuel cell, as longer as the mission, it's better in comparison to lithium batteries. It's similar, yes. There's about factor of 2. Okay. So I will focus my lecture on nano-related issues. And here we discuss the catalytic-related problems preventing widespread usage of dikemethanol fuel cell and diethylene glycol fuel cells. Dikemethanol fuel cells just started coming into the market. You can purchase them. There is one company that really produced them in series. There are many startups or other large companies trying to develop it in the last 10 years. There is only one commercial, you can eat commercial unit or commercial company that produce it, and you can purchase it. And the reason is it's very complicated and expensive. So now I need my glasses. Platinum is used on both sides of the fuel cell, and both electrodes. And we have membrane and two electrodes. We call it membrane electrode assembly. And the loading of platinum is very high. It's about 5 milligrams per square centimeter. This is too expensive. And we need to reduce it in one order of magnitude. So far it was found for methanol that platinum-ruthenium 1-to-1 bulk atomic ratio is the best for methanol oxidation. But it doesn't say what is the surface composition of the catalyst. The company sell you 1-to-1, and that's it. But for scientists, it's more interesting to know what's going on the surface, because the bulk doesn't affect very little the catalytic properties of the catalyst. You want to know what is the correlation between the surface and the activity. So platinum is one order of magnitude larger in cost than ruthenium. Therefore, we like to work with Ruthenium-Core and put on top of it platinum-ruthenium shell. Now, very few papers report on the correlation between the surface composition and the electrochemical activity. You need the material that can stand the corrosion environment of the fuel cell. And it's either very basic or most cases it's acidic. And sometimes it's under ATC. And there are very few metals that can stand this kind of corrosion. Ruthenium is one of them. It's not the only one. We are using different materials too, different metals too, or alloys, but this talk is on ruthenium. There are two problems in durability. One, there is an anode corrosion, anode catalyst corrosion, mainly the ruthenium is corroded. And there is a poisoning effect of the COC species. As you saw, when oxidation of methanol ethylene glycol, you get many CO species, and this poisons the platinum and both electrodes, and that's another problem. Now, ethylene glycol has a potential advantage over methanol, and the most important one is that it has higher boiling point, close to 200 versus 64.7. Methanol is very volatile and danger can catch fire. And ethylene glycol is well known. You know that the major constituent of your antifreeze is ethylene glycol. So you have it in any gas station today. Methanol, you have to make all kinds of regulation because it's poison. So I'll skip it. This is the major issue. Here you see ethanol does not, you cannot convert it 100% to CO2. It's not under normal conditions. So it's not a fuel, according to my definition, because you get a lot of acetic acid and acetaldehyde, and your solution become rich in this species, and you have to wash it and put another one, so that's not a real fuel. So you see the reactions, and the interesting issue is that we want to know what is the surface, the best surface relation with atomic ratio of platinum-ruthenium. So what is known today in the literature that methanol needs between 1 to 3 atoms of platinum to bind to it in order to get PTXCO species, that's intermediate. Now the other reaction that takes place is oxidation of water, and here we use ruthenium, got ruthenium OH, and then these two species react to give back platinum, pure ruthenium, and CO2. Now, the reason that we use ruthenium, because platinum for reaction number 2 is not effective. And it takes place only at very high overpotential of 0.75 volt, when using ruthenium, it's only 0.25 volt. Therefore, we have ruthenium for oxidation of water. We have platinum to oxidize the methanol or the ethylene glycol, and you have both of them. Now, the question is, what is the ratio between them? Then I just show you that ethylene glycol electrooxidation is very complex. You see a lot of species, and actually this was presented 10 years ago. We found that this mechanism is not, need some correction, and this is some of our correction. Other correction are not coming to it. So, as I said, the problem is a cost, and this is the problem also today for the hydrogen-oxygen fuel cell. In the car industry, the fuel cell is good, and the performance is good, and there is a cost issue that you have to reduce the cost by a factor of 10 or 5 at least. And the same is for direct methanol fuel cell. We are looking for lower cost catalysts. So we're using, in this case, Ruthenium-Core, and on the Ruthenium-Core, we plate platinum-ruthenium layer or shell. Now, we have two questions to ask. What is the best shell structure? Is it platinum island near ruthenium island? That means sub-monolayer of platinum, some nanosite. We have a ruthenium core. Then we put on top of it mosaic of ruthenium and platinum-ruthenium alloy. Or randomly distributed platinum-ruthenium alloy on the ruthenium core. So we want to know what is the best for electrooxidation. So we use XPS and cyclic voltammetry for the characterization of the surface. And we found that cyclic voltammetry is a very effective tool to measure the composition and the structure of the surface. And this may be good for any nanoist studying small nanoparticles. Yes. But, I mean, the way we produce it, sometimes it's amorphous, sometimes it's crystalline. It's different, depending on the synthesis. Now, this is cyclic voltammetry, and I'm not sure, but probably you don't know or you're not familiar with that. So what we take the electrode, and we run voltage from 0 to 1.2 on top of it. I mean, applied voltage to that at a rate of, let's say, 10 millivolts per second or per minute. And we measure the current. So let's say if we start here, this is what we call double layer region. Here there is no oxidation reaction taking place on the platinum, only charge and discharge of ions. Then if we go to, let's say, 0.7, so that we start making platinum oxide on the surface, oxygen evolution, and here we have reduction of the platinum oxide. And when we're going back here, we get under potential deposition of H atoms on the platinum. Each platinum atoms get one H. And this is before the potential for hydrogen evolution, therefore it is called under potential deposition of platinum of hydrogen. And then we oxidize the PTH or MH, and according to this, the area on this peak, we calculate the electrochemical surface area. That means how many atoms of platinum, let's say, we have on the surface in terms of square meter per gram. Now, on the right side, you see the same cyclic voltammetry, but we have here also ethylene glycol, and this is the oxidation of the ethylene glycol. And when you push the potential more positive, you start getting a high current. And then there is a poisoning of the catalyst, and the current goes down. Now, when we go back, there is reactivation of the surface, and we picked the 0.45 volt as the indicator for the activity of the catalyst, because at this potential, the anode of direct methanol fuel cell, direct ethylene glycol fuel cell works. So we are not working here, we are working in here. So therefore, this is the measured factor that we compare to compare the activation of the catalysts. Now, unfortunately, platinum ruthenium possess problems with the other way of of measuring the electrochemical surface area. So in this case, or in some case, we're using copper under potassium deposition for measuring the electrochemical surface area in terms of square meter per gram of the platinum-ruthenium alloy. Now, I listed some catalysts that we developed and some commercial one. This is Johnson Matthey high spec 7,000 and Johnson Matthey high spec 12,000. The 7,000 was the best in the market 5 years ago, and 12,000 is the best today for methanol oxidation. Now, if you look on the XPS surface atomic ratio, you see that the two commercial has a 1.67 platinum to 1 ruthenium. One in the bulk they have 1 to 1, and the other one has 1 to 9. Now we change it from 4 to 0.33 to see the effect of the surface composition, surface atomic ratio on the activity. And what you see here on the right side, the XRD shows that we have nanoparticles. Now, if you look at the right cyclic voltammetry, what's interesting is that to see the ruthenium oxide reduction peak. And this is typical. So if you get this kind of peak by cyclic voltammetry, we know that the surface contains ruthenium oxide particles. And this is the platinum on ruthenium on carbon nanoparticles alloy that catalyst that we synthesize, and the ratio in this case is 4 to 1 atoms of platinum per 1 atom of ruthenium on the surface, measured by XPS. So it's interesting to see that we have here the platinum oxide reduction peak. So this catalyst has island, submonolayer island, nano island of platinum, and also island of ruthenium. So it's a mosaic of platinum island and ruthenium island, and that's the way we analyze the surface. So I said it's a very strong tool. Now, when we cycle it, and between 0 to 1.2, we oxidize ruthenium and create changes on the surface of the catalyst. And this is a way to measure the degradation rate, one of the ways. So what you can see here, so a fresh one has a peak here. It's an indication of platinum oxide and ruthenium oxide. But after 30 cycles, the blue one, we say that there is no platinum on the surface, very minor. We formed platinum-ruthenium alloy, and this is the reduction of the oxide of platinum-ruthenium alloy. And here we still have the reduction of ruthenium oxide. So after cycling, what you can say that this platinum-rich 1 to 4 platinum to ruthenium, platinum decreases on the surface to 1 to 3. And we formed platinum-ruthenium alloy. Now, it's interesting that by cycling of this particular catalyst, the activity at 0.45 increased with cycle time. Now, it's another catalyst, DK6A, which, again, we took XC72, it's nanoparticles of carbon. On that, we deposit ruthenium, nanoparticles, and that we deposit platinum. But in this case, we have different ratio. It's platinum poor, ruthenium rich. It's ruthenium 2 to platinum 1. Now, I plot here on the left side cyclic voltammetry of both the high spec 12,000, which is the best catalyst available today. Maybe companies have better, but we cannot purchase it. So what you see that you have only, or majorly you have in the high spec 12,000, you have the peak that of the reduction of oxide on platinum ruthenium alloy, as they claim. But they have some solders, and maybe you have here some, I'm sorry, here maybe some platinum reduction, platinum oxide, very minor, and here for ruthenium oxide. But our one, which is ruthenium rich, is the black one, and you see that it doesn't have platinum oxide reduction peak at all. That means it doesn't have platinum on the surface, although not pure platinum, not island of platinum, although it's platinum 1, ruthenium 2, we cannot see platinum island on the surface. What we do see, we see ruthenium island of ruthenium on the surface and some platinum-ruthenium alloy. Now, with respect to oxidation of methanol, I got some question in the middle. Okay. With respect to oxidation of methanol, we see that it's a very good one, the high-spec 212 Johnson-Matthey one. You see the higher current than our. And if you look here, we analyze in two terms. One scientific, ampere per square meter of the catalyst, and it's 8 to 1.4. It's much more active. And also with respect to dollar value, ampere per gram of platinum, it's 3 times better. However, if you look on ethylene glycol oxidation, we see that our catalyst is much better than a commercially available Johnson-Matthey. And the surface activity is similar. But the dollar activity, ampere per gram of platinum, is always, our homemade is twice that of the commercially available. Here I summarize the various catalysts, and what I want to show is two things. One, in terms of surface activity, then the two best are the commercial, and one is the MA1. Over here, it's very similar. But in terms of practical or economic, our DK4A has much higher current in terms of ampere per gram of platinum or per dollar than any commercially available. In ethylene glycol, I will just come to dollars because I don't have time. So the DK6A is the best in terms of dollars, and it's almost 2 times better than the commercial one. Now to summarize, we studied several Ruthenium-Core, platinum-ruthenium shell, nanoparticles for electro-oxidation of alcohols. We show that these core shell catalysts have a potential to drastically reduce platinum loading currently needed for direct methanol fuel cell. And the work is progress. I'm not saying that the conclusion are finals because we have to study other ratios. 2 of our catalysts show superior performance in terms of activity per gram of platinum. The most active in terms of ampere per square meter methanol ethylene glycol electro-oxidation catalyst found to be platinum rich, platinum to ruthenium 2 to 1, 2 platinum to 1 ruthenium, and it is alloy shell. And this is agreement with the suggestion for the oxidation mechanism that means that oxidation of the metal molecule, the CO species has to be binded to 2 atomic platinum, and then we have 1 ruthenium for oxidizing of the water. The best in terms of ampere per gram of platinum ethylene glycol electro-oxidation catalyst was the ruthenium rich, 1 platinum to 2 ruthenium, and it consists of ruthenium island and platinum ruthenium alloy island. Now, by accelerated aging, we found that there are 2 different mechanisms of degradation. In ruthenium-rich shell catalyst, ruthenium corroded, and the alloy is segregated into platinum, and ruthenium nano-size island, while in the platinum-rich shell, the amount of platinum decreased, and the platinum and ruthenium island combined into platinum-ruthenium alloy. All of them are sub-monolar platinum. All the catalyst study is Ruthenium-Core with less than 1 monolar of platinum. Thank you for your attention.
I have a nano question. How were the nanoparticles fabricated, and how did you do this electroless deposition on the nanoparticles, and how were the nanoparticles dispersed and kept in the fuel cell? Why weren't they slipped through the membrane or whatever?
Okay. So first we produce most of it by electroless deposition layer by layer. So we take XC72 nanopowders, it's about 30 nanometer carbon powder. And with the
carbon powder?
Okay. Carbon powder. On that, we electrolyze deposited ruthenium nanoparticles in solution, wet chemistry. On that, we plate nanoparticles of platinum. All of it bind by Nafion on the electrode to make a porous layer.
You mentioned corrosion at temperature.
Yes.
It's because of exothermicity of the reaction, or I mean, what's the reason for the high temperature?
In order to get high power from any fuel cell, you have to work at higher temperature, because at room temperature the power is smaller, and you want to have a small unit, light unit. Therefore, you run it at ATC. It's also easier to get rid of the water. And ruthenium gets corroded at that temperature, and this is one of the major problems of the direct methanol fuel cell. And this is one of the reasons why we don't see it in the market, only by one company. That actually what this company did, it's over-designed. They're using very large stack, a lot of platinum ruthenium, and you can run it 2,000 hours continuously, the direct methanol fuel cell of this company.
One last question, please.
The comparison between the lithium-ion batteries and fuel cells looks very promising. However, we don't see many fuel cells around us. So what are the current main disadvantages of fuel cells? Because it looks very promising. And maybe in this context, what is your maybe biased opinion about the commercialization of fuel cells in the near future?
Well, that's a very broad question. As I said, with respect to technology, hydrogen air fuel cells can meet the target of size and weight. And today, electric vehicle using fuel cell maybe 100, 200 kilogram heavier than the regular one, and they have a range of 500 kilometer driving range. With small portable application, you cannot use hydrogen. So you use, in this case, we're trying to use methanol or ethylene glycol because it's easier and more convenient. The issue there is long-term stability. Another problem is to control the amount of water. That's quite difficult at small size. It's large size, it's less difficult. And the cost of catalyst. This is the major issue. With 5 milligrams per square centimeter, you cannot compete with lithium-ion. And the issue is that customers don't care if you give them another 5 hours. They will patch the box if this box is lower cost than lithium-ion box. So that's the issue. In order to get there, you have to reduce the amount of platinum to less than 1 milligram per square centimeter. And if this is successful, then it will be more in the market. Today there is a company that's selling about 10,000 direct methanol fuel cells per year. And it costs $5,000, 65 watts. So that's a big box, 10 kilogram size. It's not the 1 liter that we're trying to develop.